Welcome students, and we will continue in this video the existence and uniqueness theorem proof. Okay, so the existence and uniqueness theorem. So before you do that, let us just write down what the result is, and then we can go from there. Okay, just to as a reminder. So this existence and uniqueness theorem is also called the Picard's existence and uniqueness theorem, and it actually deals with system of equation. Okay, it basically says that given f in C1 of Rn, okay, C1 of Rn and x naught in Rn, okay, the initial value problem x prime equals to f of x at the point 0 is x naught. I mean, I am writing it to be 0, you can write it to be some point also, okay, it's not a problem. So x at the point 0 is x naught. This initial value problem has a unique solution. Okay. Solution. What is the unique solution? The solution exists everywhere, right? For all, it depends on where you are taking your t. T is the variable on which x depends. Okay, so let's say if you are taking t to be in some interval I, the unique solution exists in the whole interval I. Here. Okay, so now let's just look into the proof of the theorem. So essentially, we will do. We have some idea of how to prove this thing, right? Because we looked at it in the other, when we talked about first order equation. Okay, so let's just say that some interval. Okay, so let's say I be an interval where we are taking this, x is defined. So basically, and let's say x is from I to some set O. Okay, and this satisfies this equation. So you do understand x is a column vector. It takes a value for every t. So what is x doing? You see x of t. This is a n cross 1 vector, right? So essentially, that is an O. This O. This is a set which is in Rn. Clear? Okay. So if it satisfies, so this is a small note. See, if there is a x which satisfies, x prime of t equals to f of x. Okay. If it does that. So for all t, f of x t, let's write it like this, x of t, okay, if it does that and such that x0 equals to x naught, then you can use this thing, the fundamental theorem of calculus, to actually indicate this thing between 0 to 2. Now if you do that, that will give you x of t equals to x of 0 plus 0 to t capital F of x of s ds. Clear? Okay, that is what we are going to get. So basically, and let's say that's so this is your original problem 1, and the problem, this is the 2. So this 2 is called the, as you guys already know, this is called the integral form of 1. Okay, integral form of 1. Okay, now, so you do realize that this can also go the other way. So basically, if there is a x which satisfies this thing, then that x will also satisfy 1, right? So if there is a x which satisfies 2, that will satisfy 1, and again if there is a x which satisfies 1, it satisfies 2. So essentially, you can actually say that, you see, these two 1 and 2 are kind of equivalent. They are actually equivalent statements. Okay, just one is in terms of a derivative and another one is in terms of a integral. Okay, now so before we move on with the proof of this thing, let me just write down some notations. Okay, so first thing first, omega rho, these will be defined as a closed set of radius rho greater than 0, centered at this point x naught. I hope this is clear. X naught is a point in Rn. I am taking that point and I am taking a set with radius r. So basically think of it as a not set but ball. If you want, you can just think of it as a ball. It's not a problem. So it's closed ball, okay, of radius rho. Okay, and the Lipschitz constant, see f is C1, so basically you have a Lipschitz, it is locally Lipschitz, right? That's what we looked at last class, not looked at, but that was part of an assignment. So essentially that's a locally Lipschitz. Okay, so let's say that for this omega rho, k is the Lipschitz constant in omega rho. I hope this is clear. Okay, see, this rho, if you change rho, k will change. It may change, yes, depends on f, but generally it will change. Okay, so rho, so k is corresponding to that rho. Clear? Okay, number 3 is what I want a bound on f of x that will be given by m, and where is this bound? On omega rho. Okay, omega rho, see, that's a closed set. Okay, f is a continuous function, of course this is C1 function. Okay, so there is a bound in there. Okay, now, and number 4, we'll also choose something like this. See, we'll choose a to be less than, right, it is minimum of rho by m. Okay, rho by m, rho by m is the maximum, and 1 by k, Lipschitz constant. Clear? Okay, and let I is minus a. Okay, so this is the I which we will be talking about. I hope this is clear. Okay, so this t I am taking to be from I. Okay, right. Now let's just look at the proof of this thing. With this notation, we will just always, I am not going to explain to you again what is rho, what is m. So if I am using m, I will consider it to be the bound of f. Okay, and subsequently a will be the minimum of rho by m and 1 by k. Clear? Okay, so as you know that we can actually define something called a Picard's iterate, right? To do this thing, to proof of Picard's existence during existence theorem, we use something called a Picard's iteration. So what is Picard's iteration? Okay, we have covered this thing properly, so now I am just writing it down. The first iterate which I am going to write, so let's just write down the first iterate, u naught, let's say, of t, yeah, the first iterate. So that is basically your initial. So you start with the initial condition that is given by x naught. Clear? Okay. Now for t in I, define u1 of t. Clear? That is x naught plus 0 to t capital F of u naught of s ds. I hope this is clear. Now, you remember from the integral equation, see the integral equation f of x is ds, x I am taking for x1, I am taking here f of x naught. Okay, for x2 I will take f of x 1. Okay, so basically xn I will take f of x n minus 1. So basically I have information on the other the just previous u naught, right? I will just use that u naught and I will define a new u1. That's what I am going to do. Okay, now since mod t is less than a, see here we will see why this condition is required. Okay, why what is the need of this condition? See, since mod t is less than equal a, okay, and mod of x naught is less than equal m, right? That's what given to us. Okay, now if that happens, then u1 of t minus u naught, let's just see what happens to this. This is, see, x naught and x naught is gone, so basically I am left out with 0 to t capital F of u naught of s ds. Clear? That's what I have. Now you guys already know that mod of integral of something is less than equal, that can be always denominated by the integral of mod, okay, ds. I hope this is clear. Now if that is the case, you see what is the bound on f? Bound on f is m, right? Okay, so so basically if I take this m out, see, f has a maximum bound, right, which is given by m. So if I take this m out, okay, I am left out with 0 to t 1 ds, which is t. the maximum of t is a, so it is essentially a times m. Clear? Okay, now you see a times m. So a is the minimum of rho by m and 1 by k. So a is always less than rho by m, less than equals to. Clear? So a by m is always less than equal rho. Okay, that's always there. So this is always less than equal rho. I hope this is clear. Okay, therefore see u1 of t, that is in omega rho. Okay, that's the whole point. See, I want my new iterates. You see, you cannot have, I mean, you want your new, so basically you are starting out with some of closed set. Okay, so u naught of t is some in some row, omega rho, let's say. You also want all your iterates to be in omega rho. Okay, that's one important thing, and that is why you need that condition. I hope this is clear. Okay, now of course by induction you can show that I mean, you know, okay, let me write it down. By induction, this part I am not doing, you guys can try it out if you want. So I can of course show that uk of t minus x naught, that is going to be less than rho. Okay, this holds for all t in I. Clear? Okay. Okay, so we are not bothered about it, that's fine. So basically what is said is this, you see uk of t, they are well defined functions, and such that the difference between uk and u naught is always, I mean uk is always in the ball basically, okay, with of radius rho. Okay, now you see, now let uk plus 1, okay, of t is x naught plus 0 to t capital F of uk of s. There is nothing to let, so it is essentially this only ds. Okay, now so I will use induction. Okay, so essentially you see this is true by induction. I mean, not by induction, what do I say? I mean I will use induction. To use induction, let me write it to use. Okay, to use induction, let's just start with ukt minus x naught is less than equal to rho. Okay, I want to show that this is also uk minus plus 1t minus x naught is less than equal to rho, right? Let's just do that. So essentially you see uk plus 1 t minus x naught, this is less than equals to integral 0 to t mod of f of uks ds. Clear? That is true. Again, I mean, the same thing. I mean, there is nothing much to do here. So we m times t here, which is less than equal, sorry, m times a. So t can be dominated by a. Okay, a, which is again less than rho. That's the exact same thing will work. Huh? So I mean, this is okay, fine. Huh? Now we also need to prove another estimate on this thing. So essentially you see, you remember that we have to prove, you know, means I want to look at, see, this is like a sequence, right? Iteration, we are using iteration to find out a sequence of functions, and actually what we want that sequence to uniformly converge to some function. That function will show is the required solution. Is this clear? So for that, what we are going to do is we want to prove. I'm not proving this thing right now, but I'm just writing it down. We want to prove that there exists L positive. Okay, that's some constant such that for all k greater than equal 0, uk plus 1 times t minus ukt, okay, this is less than equal a k whole power k times l. I hope this is clear. Okay, I want to show something like this. Okay, now see, so yeah, so now how to produce that L? Okay, so now see, define the maximum of u1 of t minus u naught of t, yes, over minus a. Let's say that maximum is given to be capital L. Okay. Now, you see, if this is capital L, okay, then therefore what you have is u2 of t minus u1 of t, that can be written as integral 0 to t f of u1 of s minus f of u naught of s, okay, and ds. This is clear. All right. Now you see, we will use something called, so f, you see here, so up till here we did not use any property of f except that it is, you know, continuous. So essentially up till here, you see, if you want to do up till this point, we do not need anything except the continuity on f, because we were just using the maximum. You see, where is it? Yeah, we just use this property of f. Yeah, of course. So for this property to hold, we only need continuity. Okay, so basically continuous function, closed bounded set, that has attains a maximum, that is your n. That is what we are using here. Up till here we did not use any Lipschitz continuity on it, only continuity. But here we need to write down this in terms of u1 minus u0, because you know this is what we know. Maximum of this is less equals to L. Okay, so if I use this Lipschitz continuity here, what happens is this Lipschitz continuity actually works out to be 0 to t. See, f can be dominated by k times u1 of s minus u0 of s. I hope this is fine. Huh? See, this is the reason we need something like a Lipschitz continuity. This will actually, you know, break that mold. I mean, I can get from f to u. Okay, f of u to u. This is where Lipschitz continuity. This is where Lipschitz continuity is required. Okay, right. Now I hope this is clear. Now if you just calculate it, okay, maximum of this is L. So this is essentially a capital K L. Okay, why a? Because the maximum of mod t is less than equal L. Right. Now here I am going to leave out one small detail. I want you guys to do it. So basically what you need to show is you need to use induction to show this one, star. I showed u2 minus u1 is bounded. Now you use induction to show star. I hope that will be clear. I mean, you guys can handle it. Okay. Now see, I want to, you know, if you remember the uniform continuity, basically I want for some rs, okay, ur of t minus us of t, I want to make it small, right? How do I do that? So that particular thing, this is for r is greater than equal n. Okay, so basically I am choosing r and s extremely big, and this is for given epsilon greater than 0. You realize what I am trying to do? I am trying to show, you remember what is uniform convergence, right? Uniform convergence is if you go sufficiently big, I mean if you go on n. So basically you have a sequence of function un. If you take n's to be sufficiently large, right, then for any t, the maximum of up and uq for any t, that you can actually bound it by some epsilon. That's the point of uniform convergence, right? So here also we are going to do something like this. So okay, I'm choosing an epsilon and I'm taking r and s to be sufficiently large. Okay, I mean I don't know what n is, but it's sufficiently large, it's very huge. Huh? So these can of course be made less than equal k equals to n to infinity. Clear? uk plus 1 of t minus uk of t. I hope this is clear. Why is this true? I mean, why can we write it like this? Because I mean, this is just a triangle inequality. We did one. I mean, there was one problem in the assignment also, something like this, same sort of concept. Okay, so if you are not convinced with this result, how to come from here to here, I really want you to look at this. See, this will not only develop your idea of ODEs, but it will also be very essential to brush up your analysis part. Okay, so please look at it. If you are not convinced here, look at it. It's not difficult. I mean, this is very easy. You just write it down and break it up. Okay, use triangle inequalities, and you have to pass to the limit, of course, but I mean, those can be taken care of. So now this is less than equals to, okay, summation k equals to n to infinity, clear, alpha power k. Yes, you see here, from here, alpha, I will define what alpha. Alpha is basically ak, but I mean, let me just write it down. L. Okay, where alpha, okay, let me write it. So this I am choosing it to be less than epsilon, where one second, ak equals to alpha. This is what I am defining. There is nothing special about this thing, but this is what I am defining. Okay, fine. Clear? Yeah, this is fine. Yeah. Why is this true? Because of the uniform convergence. We just showed that uk plus 1 plus a, this star. We just, in star only, it's just there, right? I mean, it is it shows that basically, I mean, if you can make ak power k times l is sufficiently small, then essentially you have the Cauchy convergence. Okay, so that's what we are trying to achieve here. Okay, so now okay, what do you have now? See, u naught, what happened? One second. I forgot we used, I think. Okay, so sorry about it. See, we used u naught, u1, so we have u0, u1, u2. We have this sequence. It converges uniformly, right? That's what we proved here. See, star only proves, I mean, this I just wrote it like this because, I mean, I want to make it precise. But anyways, I mean, from star only, you can actually say that u0, u1, u2, they actually converge, okay, uniformly to a continuous function. Okay. And the capital, okay, so continuous function x from I to Rn, okay, and uk plus 1 times t, okay, this is given by x0 plus 0 to t capital F of uk of s ds. Clear? This is what I am getting for any k. Now if I am taking limits on both sides, see, limit of this thing, as a limit k tends to infinity uk, it converges uniformly. So this essentially, this part goes to x of t. Okay. Now if I am taking limit here, does not matter. This is x0 plus I have limit k tends to infinity 0 to t capital F of uk of s ds. Okay, now you see, you remember we did that last lemma in the last video. What did we say? When can you take the limit inside the integral? When you have a uniform convergence, and here you have uniform convergence, so I can take it. So x of t is given by x0 plus 0 to t limit k tends to infinity capital F of uk of s ds. This is what I have. Now, can I take this limit inside f? Do you think I mean, I can do this? Of course I can. Why? Because f is continuous. F is a continuous function from Rn to Rn, right? Or I mean, some omega subset of Rn to Rn. But anyways, it's basically a vector field, continuous vector field. Important. So what happens is f of xn will go to f of x. So for xn going to x, f of xn will go to f of x. So you see, uk is, so I can take this limit inside, f of limit k tends to infinity uk of s. Yes, I hope this is clear. The first time from here to here, how can I take the limit inside? I am using uniform convergence. If you remember the last video we did, we used linear convergence, uniform convergence to take the limit inside. Now the limit is inside the integral. Now I have to take the limit again inside f. How do I do that? F is continuous, right? So I can take that. So how do I get it? What do I get? I get x of t is given by x naught plus 0 to t capital F of x s ds. Okay, of course this is not a solution, but this is an explicit form of a solution. Okay, right. Now I hope this is fine. Okay, so since x of t, okay, since x from I to omega rho, okay, this satisfies, what is this? This is 2, right? This satisfies 2. That implies x is the required solution. Okay. Do you think x at the point 0 is x naught? Of course it is, because in that case this integral part won't be there and you are only left out with x at the point 0 is x naught. Clear? Okay, so that's there. Now, do you really think that x is C1 also? Do you think x is C1? Of course x is C1, because f is given to be continuous. F is C1 actually, yeah. And fundamental theorem of calculus says that x is C1, right? So I'm not worrying about all that. I hope this is clear. This is, I can leave it for you guys to handle. Now, I have to show that the function which we are getting is unique. Okay, so let x and y, clear, they are two functions from I to omega are two solutions, okay, of x prime equals to f of x at the point 0 is x naught. Okay, let's say they are the two solutions. Okay, now we have to show, so required to prove x of t is y of t, okay, t for all t in I. This is what I need to show. Okay, now let R is the maximum, okay, of t in I, x of t minus y of t. Okay, let's just say that this is the maximum. Now, do you think the maximum is attained? Of course it is. Yeah. Why? Because I is a closed bounded interval minus a. See, I is minus a, right? Okay. So the maximum is attained, and whatever it is, let's just say that it's attained in some point, t naught or something. Yeah. So let's say the maximum is attained at t naught. So let's say in that case R is equals to mod x of t naught minus y t naught. Yes, this is mod 0 to t naught x prime of s minus y prime of s. Yes, clear? This is less than equals to 0 to t naught mod of x prime of s minus y prime of s ds. Okay. Now f is given by x prime is given by f, so this is 0 to t naught capital F of xs minus capital F of ys. Yes, clear? That is less than equals to 0 to t naught k times. Now here I am again using Lipschitz continuity. Okay. See, you do realize that without Lipschitz continuity, nothing or none of this is possible. Okay, f is given to be C1, so it is Lipschitz continuous, not a Lipschitz continuous function, but a locally Lipschitz continuous function. I am using that local Lipschitz continuity here. Okay, so that is less than equal k times this. Yes, now what do I have? Yeah, okay, so now you see r is the maximum of xt minus yt. So I will just take this maximum here. So this is basically r times k times t naught, right? Yes, because you see the maximum of this is r, so I can take the r outside, k outside. Now I have 0 to t naught d of s here. So basically that is actually t naught, okay, and t naught is always dominated by a, so it is r k a r k. Okay, let's just write it like this. Now clear? Okay, now you see a is chosen like this. See, since a, where is it? I chose some, yeah. See, a is always less than 1 by k. So ak is always, see, from here ak is always less than 1. Okay. So if it is ak, so basically the same thing which I am using here to show that this is smaller. So where is it? Yeah. ak is less than 1. Okay. So since ak is less than 1, okay, r has to be 0. I hope this is clear. See, I am saying r is less than equals to ak times r. ak is less than 1, so r has to be 0. If r is positive, you are essentially showing that r is less than r. That's not going to happen, right? So therefore x of t is equivalent to y of t. Clear? So this actually gives you the whole proof of the theorem. Okay, so essentially let me just recall, clarify this thing. This is very, very important. I want you guys to be very clear about it. Okay, so what we showed is, we showed that, so this is like the important part. We showed that if you define a to be the minimum of, if you remember, rho by m 1 by k. Okay, of course rho m k are whatever we just did. Okay, if a lies between 0 and minimum of this, then there exists an unique solution. Unique solution x from minus a clear to some omega, okay, such that x prime equals to capital F of x, x at the point 0 is x naught. Okay, so and f is given to be in C1 of omega. Clear? Okay, so this is the result which we want. So you remember what is m? M is the maximum of f on some rho radius of omega. So basically, you take a small okay, let's say that's your x naught, this is your omega. You take a small ball of radius rho centered at x naught. Okay, and in that ball, closed bound ball, of course, m is the maximum, rho is the radius of the ball, and what is k? K is the maximum of f on rho omega. Clear? So you get a unique solution here, minus a to x. The unique solution exists here, okay, of this problem. I hope this is clear. So with this we are going to end this video.